Welcome to note set number 28, where we'll talk in a lot more detail about what we mean by linear phase and why we're able to get it through an FIR filter and how the symmetry of that filter plays into a requirement for linear phase. So this is covered in section 10.2.1 of Proacus and Monolocus. So if we define linear phase, we've alluded to what it means in the previous sets of notes. And we've usually defined our phase. Well, let me back up. So it's going to take us a while until we get to a very precise definition of linear phase. So, even though this slide says at the top definition of linear phase, it's the start of several slides that we'll have to go through to kind of nail down what do we mean by linear phase. And so one of the issues that we need to talk about here is the way we define magnitude and phase so far. So what we've been doing is saying, well, we've got some frequency response, h of omega, and if we take its magnitude, we can put that out in front, and then we take its angle. Actually, that shouldn't say arctan. A little error there I'll have to fix. So this would be angle. So it's arctan of imaginary part over the real part. So we take the angle of that. So we're basically just converting this, at each omega, convert this complex number into its polar form. Now there is a problem with this. We end up with a problem where sometimes we get a discontinuous phase when we compute things this way. And that happens when we have a frequency response that when its magnitude goes to 0, it can actually cross through the 0 on the complex plane and come out in the other side. So let's just take a look at that. So here's a real axis and an imaginary axis. Now be careful, this is not the z-plane, okay? What we're going to do is imagine looking at this h of omega up here as a complex valued function. And for each value of omega, it will be plotted. So this is really the real part of h. I won't put the rest of omega there just for convenience. And the imaginary part of h. And so for each value of omega, we'll say that this takes on some point on this complex plane. So omega equal to 0, we may be sitting here at this point. Then as omega goes to some other value, as we let omega, say, go positive, this thing may end up following some path. And then at some omega, the value of h of omega, if its magnitude goes to 0, this will actually go to the origin. So at some value of omega, maybe pi over 2, for example, this thing may go into the origin. And then as we continue a little bit past omega over 2, this might actually continue through like this and do some other path. I'm not saying that this is an FIR filter or any kind of filter that we're interested in, but that's what I mean by h of omega goes through 0 on the complex plane. As it goes through, notice that the angle instantaneously flips from this angle to this angle, and that's a difference of pi, plus or minus pi, depending on how you look at it. And so that's the actual angle, and when it does that, we get a discontinuous phase with this viewpoint. Now, if we take into account, instead of using a magnitude out in front, if we can handle this flip across here, this plus or minus pi, I mean, really that's just a negation, right? So let me try to clear some of this stuff off here. If I have, say, on this complex plane, if I have a number here and a number here, they differ in angle by pi, but they also are negatives of each other. Right? The imaginary, if I negated both real and imaginary parts of this, I'll get the real and imaginary parts of this one over there. So if we allow the magnitude to go to something that's real valued, but it can have positive or negative values, we can better account for this going through the zero or going through the origin on the complex plane without getting discontinuities in the phase. And the reason we want to do that is to just make it easier to identify and see what we mean by a linear phase. So given that discussion, here's an example of one such function that has this discontinuity in it. So very simple filter here. H of z is just equal to 1 minus z minus 1. So this is a simple two-tap FIR filter, and I'm drawing this example from Pratt's DSP book. No real reason for you to go there. I just want to give credit where credit's due. We now convert into frequency response by replacing z by e to the j omega, and we get this thing. And then we can factor out an e to the minus j omega over 2 from each term, and the purpose of doing that is to end up getting something that will allow us to apply Euler's formula. So here's that e to the minus j omega over 2 term. For Euler's formula, we would need a 2j underneath this. So we put a 2j underneath it, but then we also put a 2j out in front of it. So the 2j out in front stays there, and then this quantity with a 2j underneath it becomes a sign. So there it is, sign. And so now we can take the effect of this j and write, j is equal to e to the j pi over 2. So we can write that in polar form and then combine that with that, and that's how we get this result there. So a lot of stuff going on there to get to what we have, but we've basically written the frequency response for this transfer function in this form. And what we would normally do is say, well, all right, we're now going to take the magnitude of this. So if we take the magnitude of this thing, we're going to take magnitude of the whole thing, which would mean magnitude of the front part and magnitude of the second part. Magnitude of the second part is 1, so we can ignore that. And so we're left with just the magnitude of it looks like that. And then again, I mistyped this here. This should be angle. I'll try to fix that in the notes that I'll post. So the angle of that would cause, would end up looking like this. Well, let me back up, clear some of this stuff off. If we take the angle of this thing, we're going to have this part of it, but we'll also have a jump of pi because this thing changes its sign. And so that's what accounts for this discontinuity. So we end up getting this is a plot of this part of it, and then this thing down here it shows that discontinuity. Now, I computed this using freq-z, and I plotted it using ABS for this top part and the angle command for the bottom plot. And I just want to point out that even though MATLAB puts this vertical line here, technically it's a discontinuity there, so there isn't really a vertical line that goes up there. MATLAB puts it there because obviously I'm evaluating this on some fine grid, and at some point it's down here, and at the next point it's up there, and MATLAB just draws a line between them. As good as MATLAB is, you want to be watching and understanding what's really going on in MATLAB so that you can interpret these things appropriately. So we have a discontinuity there, and we can see that in the math, and we're now keeping track of it. So if we see that, if we look at this function down on the bottom, we might not think of that as a linear phase. It doesn't look linear. But in reality, we should interpret that as a linear phase response. And so if we use this new idea where we can represent, instead of using a magnitude out in front, we use an amplitude out in front, which it will be real valued but can go positive and negative. Then we can more properly see that we end a linear phase. So for this example, continuing on, we're going to switch from the strictly non-negative magnitude view into allowing an amplitude together with a phase view. And so if we go through similar kind of steps, we get to this point, and now we still convert the J into polar form like we did before to keep this part real, but we don't go any farther. We just leave that and we plot that. So this is a figure from Peratt's DSP book on this example, showing the plot of this, and you can see that it's positive out here and it's negative out here, and you can see that that would be the thing that would account for going through the origin, and that was what we saw was causing that discontinuity. But now, once we account for that, we end up with a plot that looks like this, and we can see that yes, indeed, this does have a linear shape to it, and so we can declare that this is a linear phase filter because its phase follows a straight line, with the phase being defined in terms of this amplitude phase view. So if we allow this new definition, we can still end up having some jumps in our plots, and these plots come from the fact that when we're computing via MATLAB or any other numerical method, it doesn't really, you compute at a point, it has no idea how many times you've really, quote unquote, gone around the unit circle. So remember that any angle, if you add or subtract 2 pi to it, you're back to the same position on the complex plane, even though you've added or subtracted any number of integer multiples of 2 pi. And so if we take a simple example here, just looking at a very simple transfer function, just z to the minus 2, we see that the angle of that is just minus 2 omega, and clearly that is a straight line. It goes through 0, has a slope of negative 2. So at omega equal to 0, we see that it goes through the origin at 0, and here's this slope. But then we see this jump, and we say, well, wow. And again, this is a discontinuity. It doesn't really exist in the middle there. It jumps, but now it continues with the same slope. This is not an issue with the mathematics. It's an issue with the computation. Whenever you compute an angle, MATLAB will put it between minus pi and pi. So in other words, numerical methods will wrap the angle back into the minus pi over pi, even though the angle, as we go to higher values of omega, looks like it should be, well, technically, theoretically, would be a number bigger than pi, or bigger than, more negative than negative pi, the numerical calculations, we say wrap it back in. So if we look at this, and let me see if I can clear this off here. So the real function of this continues on like this, and continues up like that. That's this real function. But when MATLAB computes it, it can't put something down here because that's less than minus pi. Notice that I've normalized. And so MATLAB would compute that and say, I have no reason to say that it's more negative than minus pi. I'm going to put it here. So those two angles put it at exactly the same position on the complex plane, and they differ by 2 pi. So these 2 pi jumps correspond to this so-called wrapping error. And there's a nice command in MATLAB called unwrap that will basically seek places where there's a jump of 2 pi or some integer multiple of 2 pi for that matter, and will appropriately unwrap it. So it basically starts at the leftmost position, it goes along, and then MATLAB senses, oh yes, there was a jump of 2 pi, so now it's going to take every one of these things and move it down. So now it's going along like this, and then it senses a jump of 4 pi up to the next values that it's computing. So it moves those down as well. And so that's what we get here. Now notice that when that happens, let me clear this off here again. Notice that when that happens, we don't get the right angle at omega equal to 0 that our theoretical result gives. And so we have to be aware of that. Let me just finish erasing here, and then I'll show you what I mean by that. So this function here, this function here is the theoretical phase result, and that should be this part of the line and continuing on down like this and continuing up like this. And notice that at 0 it goes through 0. That's what we would expect from that theoretical equation. This one does not, but if we actually figure out where it is, it's going to be some 2 pi shift or 4 pi shift or 6 pi shift. So we could, if we were clever, detect this scenario happening after using unwrap, and we could shift the whole thing up by 2 pi or 4 pi, or shift it down by 2 pi or 4 pi or 6 pi or whatever. But the point is that if this value is some integer multiple away from integer multiple of 2 pi away from 0, we can shift the whole curve back up and make it look like the true theoretical one. So unwrap fixes these 2 pi jumps. Unwrap does not fix these pi jumps. So what we usually do is we fix the 2 pi jumps with our unwrap, and then we, if we see any pi jumps, we might explore this a little bit more theoretically to see if it makes sense that, well, those are going to be an indication of that going through the origin on the complex plane. So we usually let our mind or our eye fix the pi jumps, but we can certainly fix the 2 pi jumps with the unwrap command. Okay, so let's go on slide here. And so now we can finally get to the point where we can define what we mean by linear phase. So after correcting for pi and 2 pi jumps, and after doing those corrections, adding and subtracting 2 pi to put the angle back into this main, the angle at omega equal to 0 back into this main range, we'll say that a filter is linear phase if the resulting phase, after all this work, in the numerical setting, but in the theoretical setting, if we have an amplitude that can be positive or negative, real valued, and we can write the phase as just some negative tau sub p times omega. And tau sub p is a real number, and it will set the slope of that linear phase. So if tau sub p is an integer, then this linear phase will impart on the signal going through the passband part of it, will impart a delay of tau sub p samples. Now, it is possible to have a frequency response with a linear phase response like this, where tau sub p is a fraction. And what that would effectively do is, you can imagine going back to the continuous time world, shifting by the equivalent of tau p samples converted back into seconds with the appropriate sampling rate, shifting it by that amount and then resampling at the actual sample points. And so this is what we mean by interpolated delay. So, effectively, it looks like you're just shifting the function and resampling it, is basically what we're talking about there. All right, moving on to the next slide here. And so now that we've got a handle on what we mean by linear phase, we can start to talk about how do we make an FIR filter have linear phase. So let's just look at the expression, the difference equation for an FIR filter. And so we know that any FIR filter will have a difference equation that looks like this. So there's only one y term, and there's a bunch of input terms, the current input term plus a whole bunch of past input terms. We can't have any future input terms, otherwise it would be non-causal. And we can rewrite that in this simple form here with just a nice summation there. So that's our difference equation for an FIR filter, and the B sub k's are called the filter coefficients, although sometimes we refer to them as the filter taps. You might remember we had a block diagram that looked like this, Z inverse, Z inverse, and what we do is we take a number off from here, take a sample, multiply it by a coefficient, take this, multiply it by a coefficient, take this, multiply it by a coefficient, and then add all those up. And so we think of these things as tapping off this delay line. So that's why they're often called FIR filter taps. Filter coefficients, filter taps, whatever you want to call them, that's what we're talking about here. And so now if we were to compare, say, whatever the impulse response is of this, if we were to, we would know that we would convolve H with X to get the output. So if we write out if we reinterpret this like this, we can see that the H of K's, while we see the summation looks the same, we see the X's look the same, the H of K's, the impulse response values match up with the B sub K's. And that's why we can call this particular filter a finite duration impulse response, because the impulse response has finite duration. So basically, you go back up here and you say, okay, I've got m of these coefficients, and so it's a length m FIR filter, and these values, the B0 out to the BM minus 1, they are the values of the impulse response, and it's 0 before then and 0 after that. Okay, so then we can also write out the transfer function. We've done this before, but we're reiterating it here. We can write out the transfer function for this FIR filter. So we just write it out just like that, and we see that the B sub k's that we had up here just show up naturally there. And then converting into the frequency response form, we see that the B sub k's also show up there. So just reiterating some of our structures specifically for the FIR filter K. So the claim is that an FIR filter has linear phase as we've defined that if its impulse response, which we now know really means just the filter coefficients, has symmetry about its center. So remember, we're talking about causal, so we're starting at n equal to 0, and we're going out to m minus 1, so we have a length m filter. And so basically what we're doing is we're saying h of n compared to counting from the end of it. So the last value is h of m minus 1. So if we put in 0 here, we'll have h of 0 must be equal to either plus or minus h of m minus 1. So, so we can see that that matches here and here. So that's what those red arrows are showing, that we must have symmetry between the two outside samples, and then the next two in also must have symmetry, and so on until you get to the end of this sequence, and you see that there is a difference whether you have an even length or an odd length. So for an odd length, you get down to the point where the last pairing is with itself. With an even length, you have one final pairing and it's not with itself. So that puts a constraint on the odd length filters. The middle filter coefficient must be such that, clearly for the even symmetry characteristic, or this symmetric versus anti-symmetric, is not a problem. We're simply saying this equation simply says H4 equals H4, so that's not a big issue. Where we have an issue to address is when we have an odd length with the anti-symmetric characteristic. And so when we have that situation, for m equal to 9 case, we'll be saying H4 must be equal to negative H4. And so the only way to get something equal to its negative is to have that something be 0. So what that says is that for an odd length anti-symmetric case, this middle value here must be equal to 0 in order to have the anti-symmetry that we're talking about here. So that's something to keep in mind as we go through these further results. So let's take a look at this. I'm going to motivate this through an example rather than trying to prove this all arbitrarily. But if you can go through this example, it sets the stage and the steps for how you would do this arbitrarily. And maybe some professors might argue with me and say, well, you shouldn't be showing with these examples, you should show how to do things arbitrarily. And my argument is, look, this is how we do things in research. You don't work out the most arbitrary general result. At least I don't, and I don't think most of my research colleagues do either. You kind of sneak up on it. You're playing with it. You're checking it out. Here's an example. It generates an inspiration or an idea, and you go, I wonder if I can, take that idea and carry it over to the general case. And so that's how things are done. So let's take a look at this as an example. So we're going to take the example of the positive sign there, so the so-called symmetric, not anti-symmetric, and we'll look at a case with even length. And so let's assume that H0 is equal to 1, H1 is 2, 3, 4. Now we need to hit the symmetry And now we go down 4, 3, 2, 1. And so we see that each one of these mappings, or pairings rather, does in fact satisfy the symmetry condition. So a very simple filter, not saying that this is a good filter in any sense, some sort of triangular filter. My guess is it's not a very good filter at all, but simple to keep track of. So we write out the transfer function of this in general, and then we plug in our values. 1, 2, 3, 4, 4, 3, 2, 1. And now what we're trying to do is show that this has the shape, or has the characteristic of linear phase, because we've satisfied this symmetry condition in the time domain. So what we're going to do is we've got this highest power of -7, or most negative power of -7. We're going to pull half that power out. So we've got z to the -7 over 2. And so to get a 1 with that thing out in front, we need a 7/2 there. Then we're going to need a 7/2 times z to the -1. So we've just pulled this out, and then we've just substituted in z to the 7/2 everywhere. And this does not mean that we're skipping anything. I'm just wrapping around. So I went from z to the -4 to z to the -5. So I went 1, 2, 3, 4, 4, 3, 2, 1, and then we're done. And so now what we can do, let me clear some of this off just so that it's a little easier to see. What we can do now is combine some of these things. And so if we look at this result here, we just take the 7/2 and the -1 and combine those powers. And likewise, we do that for every single one of these. And when we do that, we'll find out that if we look at the pairings through the symmetry, so we look at the 1 and the 1 term, we're going to have a 7/2, and we'll have, if you work this out, you'll have a -7/2. And so both of those will have the coefficient 1 out in front, and then we can combine, we can put that 1 out in front of the sum of those two individual terms. Likewise, we'll have a 7/2 times -1, and remember -1 is equal to -2 over 2. So we'll have a 7 minus 2, that's what gives us the 5/2. And likewise, we'll have a 7/2 minus 6, which will give us a -5 over 2. Both of those have the 2 coefficients, so we pull the 2 out in front, and so on and so on and so on. So I think you see the structure that's happening there. And so we just group these by their symmetry. And then I just make a big jump here, but I would encourage you to work this out yourself. If we look at each one of these things that are in parentheses here, we can see a nice structure. If we take the z's and plug in the e to the j theta, or e to the j omega for the z, you should immediately be able to see that we're going to get things that are starting to look like Euler's formula. So we can convert all of those into cosine. So each one of these things will end up being a cosine term, which, by the way, is real. And so this whole square bracket thing, now we've just established, is real, but could be positive and negative. So that whole bracket thing out in front, or actually not out in front, in the back, becomes a real valued amplitude function. And so this thing here ends up being -7 over 2. Well, m was equal to 8, so it's m minus 1 over 2. And when we substitute in for z, we get the omega term there. And so look what we've essentially established. We have that for this simple example, our h of omega is some amplitude function, h sub r. So we're using this r to indicate that it's a real valued function. So h sub r of omega, That's the notation that Proachus and Montelacus use. So there's our amplitude function times the part that gives the complex nature of it, and that ends up looking like it has a linear phase. And so what we've just shown is that if we have even length with this positive sign symmetry, we, for this example, got linear phase. And you could do a similar kind of series of steps for the generic case of the positive sign symmetry with even length and show that you get linear phase by going through and you can do the same thing for the other three cases in general. And so you'll end up getting these these two different cases when you have an odd length or an even length. And we're handling the symmetry or anti-symmetry through the signs there. So you have the plus sign when you have the plus symmetry, and you have the negative sign when you have the negative sign anti-symmetry. So basically what we've just shown is that if we have an FIR filter with one or the other of these kinds of symmetries, we will get a linear phase filter. And so down here we're showing the actual frequency response structure, and we can see the linear filter or the linear phase type. And you can see that when we have the anti-symmetry, we have this little bit of an offset here. And so we allow that to be a linear phase. So it doesn't go through the origin, but it is offset by pi over 2. And so what we've basically shown is that we have we get the appropriate kind of linear phase that we're interested in if we impose this kind of symmetry. So that makes it very easy when we're designing an FIR filter. If we want to make sure it has linear phase, all we have to do is make sure our design ends up with one or the other of these types of symmetry. So we can literally constrain our design so that we get that that exact kind of symmetry. Okay, so let's go to the next slide here. Now the other thing that we can do is we can actually do some manipulation of our transfer function given these kinds of symmetry. So if we start with the transfer function forms that we showed just a minute ago, if we sub in for z inverse, so everywhere there's a z, if we put in z inverse, and then we multiply both sides by z to the minus m minus 1, we can actually show that this result holds. And from that, we can see that there's a certain reciprocal nature to the occurrence of the zeros in the FIR filter. So basically all this is saying is that the zero structure of FIR filters that have linear phase have a certain shape or a certain characteristic. So if I have a 0 here on the real axis, I will have one also on the real axis at its reciprocal. So if we call that z2, we'll have one at 1 over z2. And so that's the kind of nature of the zeros. Notice that if there were a 0 right there, we would have it's self-reciprocal. So we would have another one right at the right at that same place. Similarly, we could also have one over here and one out here, which would be reciprocals of each other, along with the self-reciprocal right on the unit circle. And then remembering that zeros that are off the real axis must occur in complex conjugate pairs. So if we have a 0 here, we must have one here just by the nature of regular filter theory. So poles and zeros occur in complex conjugate pairs when we have real valued filter coefficients. And so that's what we're assuming right now. But now each one of those has to have its reciprocal. So we have Z1 and its reciprocal would actually be over here, and Z1 star, its reciprocal ends up over here at 1 over Z1 star. So we have these kinds of patterns, and if it doesn't have to just be in the on the right half side of this complex plane, we could have these four as well. So we see that zeros must show up in certain patterns. If we have one on the real axis, we're going to have a reciprocal on the real axis. If we have something off from the real axis, there will be 4 zeros that have to occur in conjunction with that. So there will be the 0 that you're looking at, its complex conjugate, and then the reciprocal of each of those. So they come in units of 4 if they're complex, and they come in units of 2 if they're real valued. So this is also something to keep in mind, and that can be exploited when trying to develop filter designs. So the last slide in this set of notes, just pointing out that when you're constraining yourself to using these symmetric filters, you may end up paying a price. So just noting that if we have e to the j omega and we have an omega here, if we set omega equal to 0, then we have, well, that should be e to the minus j. Then we have e to the minus j0, and that goes to 1. And so we get this result that says the sum of the filter coefficients of an FIR filter gives the frequency response at omega equal to 0. Now, if the filter is antisymmetric, that means that for every value h of n, there's another one that is the negative, except for the case where you end up with the pairing resulting down to that one and just a single one in the middle, which we said had to be equal to 0. So if we sum all these things up, that one in the middle that has to be 0 has no contribution, but then these pairs end up canceling each other. So we see that for the antisymmetric case, we know that the frequency response at omega equal to 0 equals 0. And so remember, for a low-pass filter, we do not want that for a low-pass filter. We would want a low-pass filter to be high at omega equal to 0. And so what that's telling us is that antisymmetric FIR filters are not suitable for trying to achieve low-pass filter designs. Symmetric FIR filters, though, I mean, we can use those certainly for low-pass filters. So that's for low-pass, that's our only choice from the symmetry. But the symmetric ones will give us high pass, band pass, whatever we want. Anti-symmetric will give us all, we can get any of the others except for low pass. Okay, so that finishes off this set of notes, and I will see you in the next set.